Welcome back. So, in today's lecture, I am going to talk about the Galilean group and Newton's law. Okay, in this way, we are also able to understand the importance of group for the engineering problem. Okay, and I have told you that whenever there exists symmetry, then this kind of notion, group kind of notion, is somehow automatically involved because what we want that whatever law we are going to formulate, that should be consistent irrespective of the time. Okay, so some law might be function of time, some law that is not function of the time. Okay, so we are just trying to categorize those kind of law which is not function or explicit function of the time. Okay, and in the previous class we have seen that whenever we are talking about Galilean structure, then actually three things comes into picture, that universe. And universe, here in this picture you can see that universe is represented inside some kind of box. Okay, this representation also has certain kind of interpretation, that they are telling that whenever you are trying to study some kind of system, that should be closed. Closed means you have to consider the boundary also. Okay, then only you are able to understand the exact behavior of the system. Okay, after that, now another coordinate, that is time. So I have a3 is affine space. Affine space means if we will talk about the real vector space, at that time origin is fixed, and I have told you that if you are flexible enough that origin is not fixed, then that is called affine space. Okay, and in affine space I cannot able to define the addition, but at least I can able to define the subtraction, and due to that reason, based on subtraction, I can define the notion of distance. Okay, and with help of distance, what we can do, we can able to define some kind of space, okay, where distance is also there. So and I have already discussed about these kind of things. Okay, I have discussed about the universe, I have discussed about the time, and after that I have discussed about the distance between simultaneous event. Okay, and distance between simultaneous event, I have told you that since we are in a3, all events is occurring in a3. Okay, and time is just progress in forward direction. Okay, and sometime we need also in backward direction. Suppose that if I want to know that what kind of things happens in the past. Okay, and in this way we are defining the simultaneous event. Means here you can see that I have to make sure that t b minus a should be 0, and t is non-zero. Due to that reason, b equal to a, I have to make sure then only that two events are simultaneous. Okay, and after that we are able to define the distance between this simultaneous event. Okay, and after that what we are telling, that whenever we are talking about Galilean space, that space is a4 space. A4 space means where suppose that trajectory is involving, I will define that trajectory, what is meaning of trajectory or what is meaning of graph in today's lecture. And after that we are telling that Cartesian product, and here again I am assuming that origin is not fixed. Okay, so that is true for the time also, that is true for the all kind of physical variable also. Okay, and what we are telling, that the set of simultaneous event with a given event form a three-dimensional affine space A4. It is also called the space of simultaneous event. So event is going to occur in A3 space and time is another variable. And whenever we are talking about Galilean space, in that space I have A4 occupied with Galilean space time structure. It means that I have a space, I have time, and I have distance between simultaneous event, that is going to define with this kind of inner product. Okay, in Euclidean space, if you remember that in Euclidean space I don't have concept of the time. Okay, that is only difference. Now let us come to the Galilean group. So whenever we are talking about group, so obviously I have to make sure that some kind of, so all properties, not some, all property of the group should be satisfied. Okay, and we have seen that group, if that is not abelian, then that should be satisfied 4 property. Okay, and if that is abelian, then that will satisfy phi property, means commutativity also comes into picture. Now whenever we are talking about group, it means that I have to talk about set, and after that I have to talk about the operation. What kind of operation? Binary operation. We are telling this as a binary operation. We have to select. Okay, now you can see that I have fixed this set in Galilean space, that I have a space, I have time, and I have distance between simultaneous variable. So inside set I have basically three set of element. Okay, and after that I have to select the transformation such that I can make sure that all means property, that property is the, whenever we are telling that associativity, after that inverse, or after that I need another property that is called identity, and one property that is closure. So all properties should be satisfied. Okay, and basically if you see the operation is nothing but some kind of transformation. Okay, so what we are telling that the Galilean group is the group of all transformation of Galilean space which preserve the structure. Okay, it means that I am telling that I have set. Okay, and set I have defined. Set, inside set I have already told you that I have a space, I have time, and I have actually distance between simultaneous event. So you have to understand these three things: distance between simultaneous event. Okay, so this is our set. Okay, now I have to define some kind of operation such that what happens, that after performing the operation also I can preserve the structure. Structure means again these three things remains the same. Okay, anyone has confusion on this? Now one of the obvious thing I am telling, that you can consider now a space where origin is fixed. Suppose that if you consider some kind of a space-time structure like Earth. Okay, and I am assuming that my coordinate system is fixed at Earth. Okay, and at that time what happens, that a space, if you consider, since origin is fixed, so a space A4 A3 is converted into R3. Anyone has confusion why that is converted into means R3? So general space is A4. Okay, suppose some aeroplane is moving in the air, and at that place, if I try to understand the coordinate frame, at that time space is A4. Okay, but now, and I am assuming that that plane is moving with some kind of uniform velocity. That kind of things I am assuming. Okay, and some non-uniformity comes into picture. Then we have certain way to talk about how to convert that non-uniform things into uniform things. That we have certain way. Okay, so basically, if you restrict a space as a R3 and time as a R, okay, and distance as a Euclidean distance, it is possible to show that again that is some kind of Galilean coordinate space that comes into picture. Okay, so that way I have defined the Galilean coordinate space. Okay, now since I have to maintain some kind of symmetry, means whatever operation I am going to do, that should be again come in these three things only. Okay, in this space only, and due to that reason I have to maintain some kind of symmetry. Okay, and you all know that whenever symmetry comes into picture, some group kind of notion comes into picture. So whenever we are defining some kind of operation, okay, in this way you are able to guess the operation. Okay, and I hope that Newton has well aware about these kind of fact, and due to that reason they are able to guess the what kind of possible transformation one can observe whenever we are dealing with the some physical object. So what he has done some physical experiment, and they tried to take some kind of observation, and after that he gone through the mathematics and tried to correlate that such that they can generalize some kind of things. Okay, because experiment just give you the hint that what kind of phenomena is going to occur, but cannot give guarantee that if some kind of things, if some unknown things comes into picture, then what kind of output. And due to that reason, from a experiment you have to just learn something, you cannot give guarantee. Okay, it might possible that something is working whenever whatever set of input you have considered, so in that particular set everything is fine. Okay, but it might possible that if you are just outside the set at this point, then something is not fine. Okay, it might possible whenever you are doing some kind of experiment, you are able to include infinite many point, but some point is missing. Okay, at that time you are not able to understand that what kind of behavior system will do. Okay, so for that you have to give guarantee. Okay, and guarantee, in order to give guarantee, only you have one tool, that is mathematics. Okay, so you have to go via mathematics, language of universe, due to that reason people are telling. Okay, so now I am trying to understand that what kind of transformation whenever some object is moving in some kind of a space, and that space you can going to consider. Now I am going to restrict my space where origin is fixed. Okay, so that I am telling as a Galilean coordinate space. So in Galilean coordinate space, and that space is nothing but either you can write r3 or you can also, people are writing like this, like that means this is Cartesian product. So time is here or time you can shift here, but whenever you are shifting, then you have to become very much careful, means because this will give you the coordinate system. Okay, so uniform velocity we are defining like that. Okay, translation we are defining like that. So first I am defining the operation. Okay, after that, now what we have to do, since Galilean structure, I have to make sure that whatever simultaneous event, okay, simultaneous distance between simultaneous event, that should be the same. Okay, so for that I need again another mathematical tool, and you can see that at least in linear algebra we have such kind of tool. So in linear algebra, an orthogonal transformation is a linear transformation. I will define what is meaning of linear transformation, and using this tool of linear transformation you are also able to understand a lot of things. Okay, so I will ask you very simple question, and after that I will go to the, then you are able to understand why linear transformation you have to understand. Suppose you have some kind of curve in two-dimensional plane. So this is, you can assume t, and this is, you can assume ft. So now could you please anyone tell me that if we are talking about tangent at this point, differentiability at that point, then what is geometrical meaning? That is tangent at this point. Okay, anyone has confusion on this? Now suppose if I am talking about some plane where now two-dimensional plane and another independent variable, and suppose I have now this kind of a structure. So now could you please tell me the geometrical interpretation of the derivative at this point? Anyone? What is geometrical interpretation? Ayush, what's, could you please guess? Or Amit or Asutosh, anyone? Could you please guess what is interpretation of derivative whenever we are in higher dimensional space? Kartike? Okay, Antara?
I'm not sure in 3D space.
Okay, so actually you can see now that in one dimensional space everything is easy. Okay, in three dimensional space, if you see the expression of derivative carefully, then that is nothing but some kind of things, some kind of plane kind of things that comes into picture. Now direction of plane is not fixed because several plane is going to touch here, but whenever we are calculating derivative I have to make sure that that should be unique. Okay, so for that it is possible to show that whenever we are talking about derivative in higher dimensional space, so that will give us some kind of best linear transformation about this point. Okay, anyone has confusion? And due to that reason we have to understand linear transformation, otherwise we are not able to understand that what is physical interpretation of derivative in higher dimensional space. Okay, one dimensional space is most of time that is very simple. Okay, but using linear transformation I can able to define derivative in the higher dimensional space also. Okay, so and how to find linear transformation I will tell you when I will talk about the linear transformation. Okay, so for time being you can just assume that linear transformation is, why linear transformation we have to learn, because I want to understand the physical interpretation of derivative in higher dimensional space, and here I am going to talk about some kind of orthogonal transformation, and this is very special class of linear transformation. And you can see that transformation, what they are telling, that if you apply on vector space, then you are again remains on the vector space. Okay, and on a real inner product V that preserve the inner product. It means that what happens, that if you take the inner product, if you see carefully, that inner product, most of time I am talking about the distance. Whenever I am representing, you can see here that using the inner product, I have represented the distance between two simultaneous event here in this way. So most of time inner product is nothing but some kind of generalization of distance only. Okay, so what kind of message I am going to give here, that after transformation also, okay, you can see here that if you take inner product, means if you see the distance between u and v, or if you see T is orthogonal transformation, some kind of orthogonal transformation, so if you see the distance between these two, that remains the same. Okay, so in this way I can give guarantee that if I have simultaneous event, okay, in some space or transform space, that both remains the same. Anyone has confusion? Okay, now let us try to see that how to talk about the orthogonal. So I have just give one or two slide introduction of orthogonal transformation, because first time that is appear. Okay, now what I am telling, that suppose you have in R2 means I have two axes, that is x axis and y axis. Okay, so you can see that any point in this space I can represent like this: x 1 0 plus y 0 1. Okay, and now if I vary x as a real number and y as a real number, so I can able to map any point in this space. Okay, so basically this is called basis. Okay, basis means number of independent vector, using that I can able to span the whole space. Okay, so minimum number of vector. Okay, so could you please guess the basis in three-dimensional space? Anyone? Quickly, please. Could you please guess?
1 0 0 0 1 0 or 0 0 1.
Okay, now that is perfectly fine. In this way also I can guess basis for any dimensional space. Okay, so now second question is that is unique or non-unique. Suppose here 1 0 and 0 1 I have written. So is it possible to replace this by another one, and again I can span to whole space?
Yes, sir.
Yes. And due to that reason I have infinite many coordinate system. Okay, so basis is never unique, that is non-unique. Okay, so in this particular problem what I have done, I have taken the standard. Standard means Euclidean standard basis. Whenever I am telling, at that time we are talking about this kind of basis only. Okay, now 1 0 and 0 1 I have. So what I am telling, that I have a standard Euclidean product and a standard basis. Okay, so a standard Euclidean product means suppose that if I will write x transpose y. What does it mean? That if I have x as a x1 x2, this kind of vector, and y1 y2, then y as a y1 y2, at that time I am going to understand like that: x1 multiplied by y1 and x2 multiplied by y2, like that I am going to understand. Anyone has confusion? R1 into C1 I am going to do. Okay, now what happens, that if I have a standard Euclidean inner product and a standard basis, then matrix transformation. And in the previous class, whenever I am talking about the group, at that time I have told you that if you are rotating the coordinate axis, okay, then this kind of matrix comes into picture. Okay, from here also you are able to see, suppose here I have some kind of point. Okay, now if I have some kind of point and if I have some kind of coordinate system like this, so what you can do, initially this is 1, because projection of this point here, suppose this point is 1 1. Okay, you can take 1 1, so projection here is 1. Now if that is rotated by theta, and if you do the projection here, it is possible to show that is nothing but cos theta. Easily you can able to show. Okay, because here whenever I am talking 1 1, at that time I am talking about distance. Okay, so please try to do by yourself. So this is just projection of some point in this this coordinate frame. So I have defined this kind of transformation. This kind of transformation is also telling that if you rotate by some angle theta. Okay, now you can see that E1 is my basis. It means that I have applied some kind of transformation, that is 1G on E10 means this standard basis. At that time I am going to get this particular column vector. Okay, after that Te2 means y axis 0 and y. It means that if I apply some kind of transformation on this, then I will get this kind of things. Okay, so by either geometrically you can calculate, or just by putting projection also you can able to calculate. Okay, anyone has confusion? Because, and due to that reason I have taken 1 simple thing. Okay, now if you do Te and Te means if I have some kind of vector like 10 and again 01, so 10 and 10, then it is possible to show their inner product is 1. Okay, now what I have done, I have calculated the inner product in the transform space. Okay, so now again I have one Te1 and Te2. So suppose that x and y, if you calculate, then you have 10 and after that transpose of that and 01. Okay, so it is possible to show that that is 0. So same kind of things will preserve everywhere. Okay, so this transformation is called orthogonal transformation. Okay, so whenever you have orthogonal transformation, at that time what I am telling that if you take the inner product, means if you calculate distance between two things, okay, that remains the same in two other coordinate frame. Anyone has confusion? And due to that reason, if you see carefully the Newton's law, they are talking about displacement. Okay, displacement between two things. Okay, now let us come to the generalization and generalization of orthogonal transformation. Now we are in three-dimensional space. Okay, so again you can take the basis, and basis is 1 0 0 0 1 0 and 0 0 1. Okay, again what you can do, you can project it. Okay, it is very easy to see that if you rotate about the z-axis with angle theta, then this particular thing, okay, that is exactly same like the rotation on xy plane, and this is 1. If you rotate about the here, if you rotate about in this particular frame here, actually I have done some kind of mistake, one should be here. Okay, so if you rotate about the y-axis, then this kind of structure comes into picture. So if you know two dimension, then you can see that extending is very easy. Okay, and after that rotation about the x-axis, that can be represented like this. Okay, again by projection you are able to do. Okay, that is not a difficult task. Okay, so it means that if you rotate, if your frame of reference is rotated by some kind of angle theta, then again it is possible to show that Galilean structure remains preserved. Anyone has confusion on this? Now what happens, this is the example of rotation, but what I am telling that any transformation which satisfy this kind of property, okay, then I can tell that distance between any simultaneous event that remains the same. That is our requirement of the Galilean structure. Okay, anyone has confusion? Okay, now let us come to the dimension of Galilean group. Okay, so if you see the dimension, it is not very difficult to tell that dimension is 10. Okay, because it is possible to show that every Galilean transformation of a space can be written in unique way of composition of rotation, translation and uniform motion. Okay, and in the previous class I have already told you that if I have three functions, okay, and if that form 1 and 2, then their composition is also form a group. Okay, so that is the proof. So I have skipped that proof because we have already discussed about this. Okay, so in this three way I have defined some kind of function. Okay, and it is possible to show that is nothing but 1 and 2. Okay, now what happens, that just by doing that kind of composition is a group. Okay, it means that now if I rotate, translate and uniform and do uniform motion, okay, in this way, so there whatever quantity that comes into picture, that is going to form a group, okay. And dimension, here you can see that I have written 3 4 3, okay, because whenever you are talking about translation, rotation, and after that translation, rotation, and uniform motion, okay. So during the translation, one more thing, that time I have to consider, and due to that region space is increased by 1, okay. Anyone has confusion? And due to that region, 3 plus 4 plus 3 equal to 10. So dimension of Galilean group, okay, where law remains the same, okay, that is the 10. Now let us come to the, now I am going to correlate with the Newton's law, okay. Why I am going to correlate? Because what we observed so far, that I have some kind of object, okay, that object can translate from, move from one point to another point, okay, that can be moved with uniform velocity, and that can be rotated, okay. So I have three kind of things, okay. So that kind of requirement I have whenever we are dealing with any mechanical object, that I need translation, I need rotation, I need uniform velocity. Obviously I also need non-uniform velocity, okay, but I have certain way to make non-uniform things in uniform. How basically we are doing that? Could you please guess? Suppose I have some kind of non-uniform thing. How basically we are converting that into uniform? Okay, suppose whenever I am dealing with calculus, I have told you that calculus is not a new subject. Okay, so what Newton's has done, suppose they are able to understand that whenever I have this kind of regular curve, then I can able to calculate the slope, okay. If I have non-regular curve, then I cannot able to calculate the slope. What he has done, he has developed some kind of macroscope that is called limit, and after that they are able to convert this problem into this problem, okay. So what he found, that if this problem is solvable some way, then this problem one can easily solve, okay. And due to that reason, you can see that here they have just considered the uniformity, okay, and after that they are telling that if you apply the limit concept, then also you are able to capture non-uniformity also. Anyone has confusion? So most of time whenever you are formulating some new theory, you are trying to solve this simple problem, okay. Now let us try to understand some more point. Whenever I have mechanical system and I am assuming that n point moving in three-dimensional space, why we are doing so? Because we have to, and now here also you are able to understand that whenever we are designing some kind of system, suppose that if you apply some kind of force several times, you might have seen that I am telling that you can concentrate your all mass at the center of mass, okay. And here you are able to understand that why basically we are doing so, okay, if you do analysis of this. So first you try to understand that whenever some object, point object, and if that is moving in influence of some force, then what kind of representation is required. So what I am assuming, that I have some kind of variable x and r is time, and that is mapping in r3, okay, that is called motion. And if you see the motion, motion is nothing but mapping or in curve, and r is time and r3 is the space, okay. And if you see carefully, then graph is nothing but mapping, that is subset of the direct product, okay, like this, okay. I hope that these kind of things you are knowing, okay. Now I have some kind of Galilean space where time is also real, I have assumed, and space is r3, okay. So Galilean coordinate system is also graph of a motion is called a world line. So whatever line trajectory, whatever trajectory or line that is comes into picture, that I am going to tell that as a world line, okay. And actually direct product of n copy of r3 is called configuration space, okay. So why I am repeating this kind of things, whenever you are going to do some work in robotics or any area where actually these kind of things is involved, mechanics is involved, at that time you might have seen that configuration space people are writing. So configuration space is nothing but, suppose you have n point and you want to see the trajectory of all endpoint, then that is called configuration space. Okay, and it is possible to show that in configuration space each point has 3 dimension, and due to that reason n equal to 3n. Okay, so I hope that this kind of terminology now I am going to use. Okay, so this is just for the revision, sake of revision I have again introduced. Okay, now what I am telling that according to Newton's law of determinacy, that determinacy of means Newton's law. What Newton's law is telling, that if you know the initial position and initial velocity, okay, then what happens, you are able to guess about the future state xt. That kind of things he tried to formulate. Okay, so and he know the background. Okay, so what he has developed for that, first he developed calculus. Okay, so two people are developed calculus, Leibniz or that Newton. So what they found, that if I have some kind of second order differential equation like this, x dot and t is also explicitly present. So could you please tell me that how many initial condition is required to solve this equation from the theory of the differential equation?
2.
Two initial condition, that is x t0 and x dot t0. So first he has given this kind of theory, or he has taken theory from somewhere, I don't know. Okay, so he know that if I know I have measurement of x t0 and x dot t0, then I can able to do lot of things. Okay, and here this equation is autonomous or non-autonomous? Could you please guess quickly?
Non-autonomous.
Non-autonomous, because time is here, so this is non-autonomous. Okay, now what he told, that suppose that if you have to identify the futuristic trajectory of any mechanical system or any system, so you have to just make sure that you are able to measure the position like quantity or velocity like quantity. Why I am telling velocity like quantity, that even if you can take the temperature, and if you know the temperature and rate of change of temperature, again you are able to predict the temperature for all future time. Okay, similar things happens. Suppose that if you are in electrical circuit, and if you know the some quantity, suppose that I have some kind of things that is given by c dv by dt, okay, equal to something. Okay, again, since that is first order differential equation, so I can give guarantee that if I know the vt0, then I can predict the future. So if rate of quantity and that particular that quantity and rate of change is also known, rate of change, previous class I have told you that why rate of change we are assuming. Okay, because we are also assuming that whatever right hand side function that is known to me. Okay, and why Newton has just taken these two, because he was telling that this kind of things I can able to calculate based on the experiment. Okay, so there is no need to worry about the right hand side of things. Okay, so suppose that if I have some kind of object, some kind of block, and which is falling towards the earth. Okay, I know from the experiment that that is nothing but g. Okay, g is the acceleration of gravity, and how basically we have calculated this acceleration by experiment. Okay, so same kind of things he is telling, that from mechanical point of view, the form of f for each system constitute the definition of the system. Okay, so if you fix this, then actually this generalized differential equation is converted for that particular system. Okay, so what is main idea of Newton? He was telling that you can take second order equation, and suppose by experiment if you able to understand this right hand side, okay, then you are able to predict the future. So what Newton is telling, that if you have to know the behavior of some system, then you have to do the experiment also. That is the meaning. Okay, so if you have new system, then obviously if you know the x t0 and x dot t0 position or velocity like quantity, you are able to predict the future, but for that you have to do the experiment. Okay, so using experiment you can predict the right hand side, and after that you can go further. Now let us try to see some more thing, because up to here he do not talk about the coordinate frame. Okay, what kind of space he is talking about? He is just talking about the differential equation, but this differential equation can be solved in different space. Okay, so now if you become mature, at that time you are able to understand that whenever I have differential equation, then which space solution is going to lie. It might possible solution will lie in Banach space, in Euclidean space, or some other space. Okay, so a space is very important to understand. Now let us try to understand the constraint. Okay, so what kind of restriction whenever we are going to apply Newton's law we have to follow, because I know that if I want to translate, I want to move with uniform velocity, and if I want to rotate, okay, then I need some kind of a structure, that is Galilean kind of a structure. And that Galilean structure, if I have simultaneous event, okay, then I can give guarantee that simultaneous distance between simultaneous event that remains the same. It means that simultaneous event doesn't depend on the time. Okay, so for that, what we have to understand first, we have to brought that kind of theory and theory of differential equation together. Okay, so now what I am going to do, I know that if I do experiment and somehow I measure the right hand side of this differential equation, okay, and if I measure two quantity, initial time what is position and initial time what is velocity, then uniquely I can able to predict the future. Okay, so this kind of things we are able to understand from the mathematical point of view. Okay, but where I have to do this kind of experiment, so for that a space is required. Okay, and I have to make sure that whenever some law I have developed here, whatever f I have measured, so that remains consistent in several places, okay, or all simultaneous places. Okay, and due to that reason I am going to brought the theory of relativity. Okay, and here I am not going to talk about general theory of relativity, I am going to talk about the Galileo theory of relativity. Okay, and what Galileo theory of relativity is suggesting, suppose that if I have some kind of world line I have already defined that whatever evolution of t and x, that is called world line. So if that remains like this, okay, it means that affine transformation is going to preserve. Okay, and then what happens, that whatever group structure in this space and this space, that remains the same. Okay, and due to that reason, if some object is moving with uniform speed, okay, with respect to some other coordinate frame, I have two coordinate frame and another coordinate frame is uniform with respect to first one, then it is possible to show that whatever law, that remains the same. Okay, anyone has confusion? And same kind of things I have written, if we subject the world line of all point of any mechanical system to one and the same Galilean transformation, we obtain the world line of the same system with new initial condition. So what we have done, I have this kind of line, so I have applied the transformation. Okay, so here, since whenever I have defined the Galilean transformation, you can see again, come back here, that we have talked about three kind of things. Okay, that is translation, and after that I have talked about the rotation, and after that I have talked about the uniform velocity. Okay, so what I am going to do, I am going to apply the rotation, I am going to change the time also, so translation, and after that motion with uniform velocity. Okay, so if you perform these kind of all these three kind of operation, it is possible to show, and here you can see that composition is rotation, translation, and uniform motion. Okay, so same kind of transformation I have actually applied to this world coordinate. So I have parallel world coordinate. Okay, and here if you see the distance between any 2 point anywhere, that is fixed. Now I have applied the rotation. So if you apply the rotation, then all world coordinate is rotated by like this. Okay, and after that I am translating means either you can do experiment t, and t plus t curve remains the same, and after that I am moving with uniform velocity. So due to that reason, this kind of pictorial view we have given here. Okay, now this impose lot of constraint, because I have to make sure that right hand side, whatever law I am predicting, that remains invariant with respect to this kind of space. Okay, and this kind of constraint, now let us come. So first constraint is time translation. Okay, so what does it mean, that suppose I have second order differential equation, So I know that if I have second order differential equation, I have certain kind of solution. Okay, that solution I am assuming that suppose x equal to phi t is the solution. So now I have to make sure that if I consider any increment in time, that is t plus s, those so same solution set should be satisfy this. Okay, and could you please guess that when this kind of things happens? If differential equation is explicitly depending on time, is it possible to give guarantee, this kind of guarantee, that if I change x phi t by phi t plus s, then that will satisfy the same equation? Obviously not. Okay, because if time is explicit, and due to that reason, what Newton has suggested, that if you are working with the Galilean frame of relativity, at that time whatever law that comes into picture, that is invariant with respect to time. So time, from the time invariance, you are able to guess that if I have some kind of mechanical system that is represented by some kind of autonomous differential equation. Okay, anyone has confusion on this? Because we have already seen the category. So this is non-autonomous differential equation. Now this is autonomous differential equation. So due to this restriction, time translation, okay, and now you try to check all mechanical law, you are able to figure out that this kind of things happens. Okay, or if non-uniformity comes into picture, at that time they are again do approximation. After that we have to make sure that that is also invariant with respect to translation. Okay, so how to make sure that something is invariant with respect to translation? So at that time I have to make sure that the relative position with respect to one object to another object, or relative velocity. And due to that reason, you can see that now suppose that I have n number of point. Okay, so n number of differential equation basically comes into picture. Okay, because what Newton is telling, that if you have one event, so corresponding to one event, you have this kind of differential equation. Okay, and since I have to make sure the time translation, so that is converted into this kind of differential equation, x and x dot, then only I can tell that this abstract differential equation, whatever we have developed in mathematics, and if I have some kind of coordinate frame, okay, I have to preserve some kind of law, so at that time they should be satisfied some kind of group kind of notion. Okay, and we have defined the group, that is with respect to rotation, translation, time translation, and after that uniform motion. Okay, and due to that reason, this kind of thing should be preserved. So it is possible to show that if I need some kind of invariance with respect to translation, then that should be right hand side should be depend on the relative position and relative velocity. Okay, so due to that reason, there is no need to explicitly calculate the position, just relative position and relative velocity. If I know, then I can able to predict the future. That is the meaning. Okay, now let us come to the last one. Last one is called isotropic space. What does it mean? That I have to make sure that Galilean transformation, rotation is one of the component, and that is also should be preserved, okay, or invariance with respect to rotation, means there is no preferred direction. Okay, so now you are able to understand that if I have object, some kind of point object, so if that will move like this, like this, like this, like this, like this, so there is not a problem. Okay, now suppose if you are taking some kind of cart, okay, then you cannot tell that cart, if cart is moving in this direction or this direction, then things remains the same. Okay, so now are you able to understand that whenever we are predicting, whenever we are applying law, then why we are converting this into this? Because I have to make sure this isotropic property, and due to that reason we are telling that whenever you are applying Newton's law, and whatever situation that comes into picture, that is ideal situation, but in physical situation it might possible your response is a little bit different. Okay, so in order to make sure that isotropic space, I have to make sure that all system, okay, should be converted as a point, then I can tell that if that is rotate also, then that is not a problem. Okay, and due to that reason, now again I have an object, and in each object I have it represented motion by phi I r plus r cube, so motion of point system, and again this, and after that I have to make sure that g is nothing but orthogonal transformation. I have already told you that because I have to make sure that whatever transformation that comes into picture, so distance between two events that should remains the preserved. So finally what happens, that whenever you are applying the Newton's law, at that time this kind of situation comes into picture. I have autonomous equation. Okay, if you have forced equation, so you have to convert that force equation into autonomous equation again. Okay, you have to make sure that whatever space that is isotopic space, so for that what I am going to do, I am going to keep everything at the center of mass. And whenever I am talking about two different coordinate frame, so relative position or relative velocity is only important, so there is no need to worry about absolute one. And time translation, I have already told you that why I am considering the autonomous equation. Okay, so in this way, whatever differential equation first coin in order to understand the differential equation, and using the coordinate frame or theory of relativity, they have told that in which situation it is possible to show that if I formulate some law that remains the same, okay, in different places. Okay, anyone has confusion? Okay, so I hope that you are able to understand that why theory of relativity is important. Okay, now what Einstein has done, that they have actually changed the structure. Okay, and they are telling that suppose that if some train is moving with velocity of light, and if some object is moving inside the train, that is some velocity v, and if observer is situated outside the train, then why velocity again remains the same. Okay, and you might have seen that they are telling that some contraction in time or something, that kind of theory that comes into picture. Okay, so now if you will try to study that theory, then also you are able to understand. Okay, so what I am telling, that several places now you are going to apply the Newton's law. So at that time you have to become very means the particular, and now you are able to understand that why I am converting some mass in the point mass. Okay, so at least theoretical point of view, you are also able to understand the theory of relativity, how that is involved in this kind of things. And due to that reason means, now you at least know that how things why things work. Okay, now how things work, so for that you have to do experiment. Okay, so if you are going to apply Newton's law somewhere and come up with the second order differential equation, so that is called mathematical modeling by first principle. Okay, so in next class I will do some examples, and after that I will move to the another thing that is called, again I am going to take the help of the calculus, and we are going to see that how to obtain mathematical modeling if I just able to calculate the energy, kinetic energy and potential energy. And again theoretical thing I formulate, and then I will come up with some example. Okay, so with this remark I am going to end the today's lecture. If you have any confusion, please let me know.